started. So in this section, we're going to do the first, what do you call it? The first lesson of chapter 7, and this is on exponential functions, right? So first, let's talk about what exponential functions are. Exponential functions are functions that look like this. F of x is b to the x. B is the base. But now b is a constant and x, which is the exponent, is the variable, right? So until now, right, our functions have kind of looked like this, plus like 2 and so on, right? Where the base is the variable, the exponent is a number. Now things are going to be switched. So you're going to have something like, f of x is equal to 2 to the x, right? The number is the base this time, the exponent is the variable. So what do we know about exponential functions? Well, the main characteristic of exponential functions is they increase or decrease very, very rapidly, right? So for example, suppose, like you come to school one day and, you're feeling fine and you haven't seen your friends for the longest time and you're like, oh, like hugging them and, oh my God, I missed you and this and that. And then, a couple hours later, like at lunch, you're like, oh my God, like my throat feels kind of ticklish, right? So you didn't know that when you were hugging all of your friends, one of them was sick, right? They had the flu or something. And then now, so you were feeling fine. You had none of that bacteria inside of you. But then now a couple hours later, all of a sudden, like there is enough that you're not feeling well, right? By the time you go home, you are just completely done for. Like you've got fevers and chills and you're bedridden. So what happened? In a very, very short amount of time, the number of bacteria in your body increased extremely rapidly, right? Just over a couple of hours. That's exponential growth. So when we graph an exponential function, this is what it looks like. And do you see how here, like, if I'm at this value for x, and if I just go over a little bit, and I go up to the y's, look at how much of a bigger difference it was on the y than it was the x. Do you see that? Like just by going over a little bit on the x, there was such a big difference in the y. That's a characteristic of an exponential function. Another characteristic of exponential functions is that they have an asymptote, which is a line, it's an imaginary line that the graph comes exceedingly close to but never touches, okay? All right, so let's go to specifics. The parent function of an exponential function is b to the x. The domain is always going to be all real numbers, okay? The range is going to be, for the default, for the parent function, the range is going to be y is greater than 0. And the asymptote is y equals 0. However, if the asymptote changes, then the range changes along with the asymptote, okay? So generally, it's going to be y is greater than, whatever the value of the asymptote is. Okay? Or it can be y is less than the value of the asymptote. Okay? All right. So how are we going to graph these then? I like to pick values for, I like to just make a table to graph my exponential functions, right? So this is y equals 2 to the x. That's the first one we're going to graph. This is like the parent function, right? It's a number to the power of x. The asymptote, like for the default case, is going to be y equals 0. So the first thing I do is I graph the asymptote, which is y equals 0. It's that horizontal line, and I'm going to make it a dashed line. Now, you're using a pencil. You've got this. How do you make it visible so Ms. Malikian can see and not deduct points? Because you'd better be sure I'm going to deduct points if there is not an asymptote. What I like to do is I just go like a hairline above it, and I do this. And trust me, my eye over like more than 2 decades has been trained so well. If there is an asymptote, I will see it, and if there is not, I will know it, okay? So just a hairline above is good enough. Okay, so now we pick points. Whenever you pick points to graph something, you always want to pick 0. You always want to pick some positive numbers and some negative numbers. It turns out for exponential functions, going from -1 to 2 is a really good set of numbers because it makes the numbers manageable for the most part. So for the first one, I'm going to get 2 to the -1, which we know is how much? 1/2. 2 to the 0, that's the y-intercept, 1. 2 to the 1, 2. 2 to the 2, 4. So here at -1, it's 1/2. 0 is 1. 1, 2, and then 2 is at 4. Now we're going to graph this. So remember, when you graph an asymptote, or when you graph a function, this is not an exponential function. This is connect the dots, like when you were in kindergarten. The characteristic of an exponential function is increases rapidly, so show me the increase, and that it follows the asymptote on the other end. So show me that it follows the asymptote on the other end. Okay? All right, let's take a look at this number, this function for a minute. This is 2 to the x, right? So basically, x is the exponent of 2. So what we're looking for here are the powers of 2. So what are the powers of 2? 2, 4, right? What's the next power? 8, right? 2 to the power of 3 is 8. 2 to the power of 4 is 16. 5 is 32. And then if you go on the other side, right? You always want to look at the powers of 2. So for example, so if here are the exponents and here are the powers of 2. So if the exponent is 1, 2 to the 1 is 2. Exponent of 2, 4, 3, 8, 4, 16, and so on. That way, exponent of 0, 1. -1, 1/2. -2, 1/4, right? So that's the number that we're graphing. Okay, so the y-intercept here is 0, 1. The domain is all real numbers. And the range, do you see how the graph sits above the asymptote? That means it's greater than whatever the value of the asymptote was, which is 0. Okay? So if the asymptote was at -2, maybe y is greater than -2. Cool? Cool. Okay. What are you doing? Right? Are you talking in there?
Yeah.
Okay. Okay. All right. That's a lot of work, but fine. Okay. I'm fine with that. Okay. So that was exponential growth. So before we move on, for exponential growth, you see how as you move to the right, the graph goes away from the x-axis. Do you see that? And what makes it exponential growth is that b is greater than 1. This number that's being raised to the exponent is greater than 1. So now let's go over to exponential decay. It's again, the same form, but now b is between 0 and 1 for exponential decay. So for example, y equals 1 over 3 to the x, that's decay, right? Because the number being raised to the exponent is between 0 and 1. So decay is the opposite situation of when you're getting sick. So suppose now you're so sick, your parents are like, okay, you know what, we got to go to the doctor. Go to the doctor, they check you out, and they're like, oh my God, yes, you need antibiotics. So you start taking the antibiotics. At this point, you've got like so much of this bacteria in you, you just feel horrible. You start taking the antibiotics, you take 1 dose, 2 doses, and all of a sudden you feel so much better, right? That's exponential decay because all that bacteria quickly died off. Now, suppose you took those antibiotics like forever, right? Will the number of bacteria in your body ever like go completely to 0? No, there's always going to be like that 1 left, let's say, right? That's what an asymptote is. Yeah, they decay towards 0, but the number never actually gets to 0. Okay? All right. So, again, like the domain is all real numbers, and the range, you know, we can take a look. Again, it's tied to the asymptote. If it sits above, it's greater than. If it sits below, it's less than. Okay, so let's graph an exponential decay function. Do you see how that's decay? Because it's half to the x. So again, I have negative 1, 0, 1, 2. When x is negative 1, 1 over 2 to the negative 1 is 2. 1 over 2 to the 0 is 1. 1 over 2 to the 1 is a half. 1 over 2 to the 2 is a quarter. Okay, where's the asymptote? Y equals what? 0. So I put that here again. And let's graph at negative. Huh? So so for the parent function, the default case, it's always y equals 0, unless there is a vertical shift, which we haven't gotten to yet. So at negative 1, we're at a 2, then 1, then a half, then a quarter. You see how it's decaying. And we're going to graph in exactly the same way. Okay? So the y-intercept is 0, 1. The domain is all real numbers. Oh, what happened here? Okay. So the domain we said was all real numbers, and y is greater than 0 for the range. All right, so let's talk about transformation. Okay, so here, right, this is our standard transformation. A times b to the x minus h plus k. So what does h do?
Left to right.
Move the graph left or right. So it's a horizontal translation. K is a vertical translation, right? And then what does A do to the graph? It's a vertical stretch or a dilation.
Are there reflections?
Okay, and then if A is positive, right, then, or let's just do this. If A is negative, it's a reflection around the x-axis. All right? Okay, good. So take a look here. This is 2 to the x minus 2. So first of all, is this, yeah.
Is reflection on the x or y?
Yeah.
Which one?
Oh, x-axis, sorry. So first of all, is this growth or decay? Growth. So, okay, so let's go negative 0, negative 1, 0, and 1. Okay, the domain is all real numbers, right? Okay, so look at this. There is a vertical shift down 2 units, correct? That means the asymptote, the vertical asymptote, is now y equals negative 2 because it has moved down 2 spaces. Okay? So now let me plug in the values. So when I have 2 to the negative 1 minus 2, this is a half minus 2, which is negative 3 over 2. Okay? 2 to the 0 minus 2, 1 minus 2 is negative 1. 2 to the 1 minus 2 is 0. Okay? So, negative 3 over 2, negative 1, 0.
What was that top equation?
The vertical asymptote in red.
Yeah.
So the vertical asymptote is now y equals negative 2 because it moved down 2. So take a look at the range. Now it's going to be y is greater than, because this is still on top of the asymptote, but it's greater than negative 2. Cool? Is that? Does that make sense? Yeah, so thank you for noticing that. Let's make that minus 2. All right? So again, we're going to do negative 1, 0, 1. The asymptote is again y equals negative 2. Huh? Oh, sorry. It's again y equals negative 2. So, okay. So here we're going to have 3 to the power of 0 minus 2, which is 1. Oh my gosh. Okay. Now we're good. All right, I'm not going to touch it. 3 to the 1 minus 2, which is... No, this was negative 1. And then this is 1. And then 3 to the 2 minus 2 is how much? 7. Okay? So here we go. We're at y equals negative 2. Negative 1, we're at negative 1. Then 1. Then 7. Okay? Do you see how much quicker this is? It's because the whole thing has been shifted to the right one, right? So we're kind of like, on the other side now. Okay. So the domain is all real numbers and the range is y is greater than 2. Okay. Yeah.
Is there no, sorry, is there no h in this one?
There is.
So
It's-
why is it affected?
Huh?
Why is it maybe?
It did affect it because that's what I was just saying. That's why it looks like it's more steep because it's kind of like shifted over here.
Oh,
That's what I was saying
okay,
before.
that's
Okay. So the next one, growth or decay? Decay, but there's also a negative in front, so this is a reflection around the x-axis, right? So now it's going to be underneath the the asymptote. So let's plug in negative 1, 0, 1 again. So negative 1/4 to the negative 1 plus 3 is negative 4 plus 3, negative 1. And then when the exponent is 0 is 2. Then negative 4 to the 1 plus 3 is negative 1/4 plus 3, which is 2 3/4, right? So for the purposes of graphing, go ahead and, if you want to do a mixed number, do a mixed number because, it's better for us to graph. Where is the horizontal asymptote here?
3.
Y equals 3, right? So when I ask you for the horizontal asymptote, you're always going to write y equals the number, right? Okay, so at negative 1, we're at negative 1. At 0, we're at 2. At 1, we're at 2 3/4. And it looks like this. Okay? Domain is always all real numbers. Even when you're like half asleep, you should have remembered. Domain is all real numbers. What's the range then? Y is less than 3. Okay? All right. So this next one, now we have a dilation as well. Right? So let's pick negative 1, 0, 1. What's the asymptote now? Y equals 5. This is also decay. So this is going to be negative 4 to the power of, negative 4 times 1/2 to the power of negative 2 plus 5. So negative 4 times 2 to the 2, 4, plus 5. Is that right? Yes? So that equals negative 11, yes. We can do it, it's fine. It's just 1 away. So negative 4, 1/2 to the negative 1 plus 5. That's negative 4 times 2 plus 5, negative 3. Negative 4 times 1/2 to the 0 plus 5 equals negative 4 times 1/2, which is negative 2 plus 5, positive 3. No? Huh? Oh, it's a 1. Right. So it's a 1. Fabulous. Okay, so -1 is at -11. I'm just going to put it here. That's fine. 0 is at -3. 1, 1. And then, so it goes that way. Okay? Domain is all real numbers. The range is y is less than 5. Okay. I'm going to say one more thing about this, but we'll come back to it in a minute. Okay. So, all fine and well. This is how the graphs look, but where do we use them, right? I gave you one example about like bacteria population. That's a perfectly, reasonable place where this applies. Another place, so basically any type of population growth, compound interest, a value of a house or a car increasing or decreasing are all places where we use exponential functions. Okay, so equations for growth and decay, right? We're going to use exponential growth. So when you have exponential growth or decay, which increases or decreases by a fixed percentage over an amount of time, you can use these equations. Now, there's a little bit of a caveat with these, like a little bit of a thing, okay? The book likes to use this notation, but I think this book that we use is literally the only place where they use this notation for these equations. Everywhere else, we either use n's or y's instead of the a's, okay? So let's talk about what this is. A of t is equal to little a, 1 plus r to the power of t. So a of t here is the final amount of something. T is the time. R is the rate in decimals, of course. Okay, little a is the initial amount. Okay, so R is the rate. So something increases at a rate of 3% per year. 1 minus R is the decay factor. So for example, if the rate is 3%, which is 0.03, the decay factor would be 1 minus 0.03. And then the growth factor would be 1 plus 0.03. Cool? Okay. Okay, hang on. In all other books, these are usually written as in two ways. N equals n subscript 0, 1 plus r to the t. Or y equals y subscript 0, 1 plus r to the t. And this subscript 0, like y subscript 0, this is initial y. We read it as y naught and naught. Okay, that's the notation. Okay? All right, Leah, you're with us? Leah, you with us? Yeah. Okay. All right. So the first U.S. Census was conducted in 1790. At that time, the population was that many, 3 million, blah, blah, blah. Since then, the U.S. population has grown by approximately 2.03% annually. Classify the function representing the situation as either exponential growth and decay, and identify the growth factor or the decay factor. All right, so let's go ahead and do this. Sorry, 1 sec. I just wanna. Oh my goodness. Okay. So what is the exponential factor here? Is the population growing or decreasing? Growing. So this is definitely growth. So this is exponential growth. The growth factor is 1.0203. Right? Everybody okay with that? Okay, so 2.03, this is like in decimals 0.0203. Because it's exponential growth, you add 1, so it's 1.0203. Huh? So when you have a percentage, how do you convert to decimal? You divide by 100, or you move the decimal place to the left twice. Okay, so the equation will look like A of t is equal to the initial amount times 1.0203 to the power of t. Okay? All right, so let's go ahead and graph that. Go ahead and take out your calculators, and let's graph that.
I'm just still confused. How do you get 1
Because you add the 1.
So this is the percent increase. How much would it be in decimal? 0.0203. Because it's growth, you do 1 plus this number. Then you do 1 minus that number. So it'll be, okay, point.
Should we keep the t as it is? Like,
Yep, you're going to use x instead of it.
It's exponent t.
Exponent of x when you graph. Yeah, this is a t here. In your equation, you're going to put a t. But when you graph on your calculator, you're going to use an x for it.
oh, I don't see it. Maybe I'll do it.
Huh?
I don't see it.
The graph?
Yeah, I need to see that.
You need to zoom out. Correct.
When we graph out the calculator, is A of t just y?
Yes. Yes. So this is going to be 39.
We don't know the time.
No, 29214 times 1.0203 to the power of x. Use x for instead of t.
All the way on the left.
So it's going to look, you're not going to see anything because these are values of like y equals like 1, 2, 3. But here we've got, right. So here's what you want to do. You want to go to menu, Windows Zoom. Let's go to window settings. So the x-axis represents the time, right? We want to make that go from 0 to, let's say, what year was this? 1790. So how many years are we looking at? Like 250, right? So why don't we go from 0 to 250, right? Well, I mean, until now, right? Like just kind of 250, 300. Okay, right, but we want to, okay. So now you still don't see anything. So what I can do then is menu, window zoom, and here go to A, which is zoom fit, and you can see a very pretty graph. So once you fix your x-axis, when you do zoom fit, it'll show you all of the y's
The window setting.
for that. The window setting, I went from, for the x's, I went from 0 to 250. Yeah.
Where's the?
So here's what I did, guys. Don't look at the y's. I went from 0 to 250 because the x-axis represents the time for this problem. Since 1790 to now, that's like 250-ish years. Okay? So, and then I pressed enter, then I did zoom fit, and that showed me everything on the y-axis. So now, this is what the graph looks like. So now the next question is, what does the y-asymptote, what does the y-intercept represent? Well, the y-intercept is when t equals 0, right? So y-intercept is the initial population. This is how much the population was at t equals 0. The asymptote is the lowest value the population will ever reach. Okay? So asymptote represents lowest population we will reach. What is the asymptote in this case? Y equals 0. All right, so let's move on.
Oh, it's initial.
Okay, so a cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12%, 12.5% of the caffeine from their system per hour. Is this growth or decay? This is decay. So classify the function as growth or decay, so we know that this is decay. What is the decay factor? So now it's going to be 1 minus what?
0.12.
Right.
0.0.
No, 0.125. Okay, so that's, how much is it? 0.875. Okay? Write the equation, then graph the function on your calculator. So the equation is A of t is equal to the initial amount times the decay factor to the power of t. And then, so now go ahead and graph this one. Okay? So tab, and this is going to be 35, and then this is, how much was it? 0.875. 0.875. Okay, so obviously you're going to have to adjust these windows. So now what does the t-axis represent? Time again, time it takes for your body to get rid of the caffeine. So why don't we do like 12 hours or something, right? It's not going to, so I'm going to go to menu, window zoom, window settings. I'm going to go from 0 to 12. And then I'm going to go to menu, window zoom, zoom fit. Do you see how? Okay. Okay, so maybe, you know what, looking at this, I want to like expand my windows a little bit. So let's go to menu, window zoom, window settings. I think I want to go from like -5 to maybe 24 hours. Okay, menu, window zoom, zoom fit. Okay, that's a much better graph. Do you see that? That's a much better looking graph. So look, like 24 hours later, you're just still like trying to get rid of that caffeine, right? That's kind of sad. Okay, so what is the question asking for? Estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup. So here we have two options. One is menu, trace, graph trace, and you can just plug in 3, enter, and it's 23.447. Right? Huh? So yeah, so A of 3, another way of doing it, okay, so there are so many different ways of doing this. So A of 3 is actually 35 times 0.875 to the power of 3. So you could have either plugged it into your calculator and gotten that. You could get it from the graph, so it's about 23.45 milligrams. Another way to extract it from the graph is this. Let's press escape. If you do Control T for table, Control T for table, you can go down the table, and then when X is 3, you have 23.45 as well. All right? Okay, I'm going to say one other thing before I stop. What time is it? Okay, nice. I'm going to say one other thing before we stop. Let's take a look at our graphs for exponential growth and decay. So this is exponential growth, okay? As x approaches positive infinity, the graph goes away from the x-axis, okay? Graph moves away from the x-axis. This is important. Take a look. We're not done yet. Write this down. Here, for decay, as x approaches infinity, the graph moves towards the x-axis. By the way, x-axis or asymptote, right? I'm kind of using those interchangeably, like the x-axis or the asymptote, technically the asymptote. So take a look here. Decay moving towards the asymptote. Growth moving away from the asymptote. Growth moving away from the asymptote. Look at this one. This is a negative, right? This is a negative, but it does not matter whether it's positive or negative. What tells us that this is decay is that as you move towards the x equals positive infinity, it goes towards the asymptote, not away from it. This is so important, okay? Like I have students in calculus who, you know, don't like see that, like that fact, okay? All right, so we will stop here. And your homework is the